In 1957, a 27-year-old graduate student at Princeton handed in a doctoral dissertation containing one of the strangest ideas in the history of physics. The idea that reality is constantly splitting into countless branches, each one as real as the one you are in. The physics establishment of the day quietly set the idea aside. The young man left physics, went to work calculating the arithmetic of nuclear war, and died believing he was right, with almost no one agreeing with him. His name was Hugh Everett, and nearly 70 years later, his discarded idea has become the working assumption of the engineers building the most advanced machines on Earth. What changed was not a new argument. What changed was that the machines got built, and they work. So what does it mean that we have built devices whose ordinary operation seems to confirm an idea that fundamentally alter the meaning of reality? Get cozy and settle in. Subscribe if you have not and stay with us, because this story moves from a quiet grave to a cold laboratory and does not arrive where you expect. Let's dive in. Part 1. The 200 Seconds. On the 23rd of October 2019, in a low building in Santa Barbara, California, a machine the size of a household appliance finished a calculation, and the answer it returned took 200 seconds to produce. That sentence sounds like nothing. 200 seconds is the length of a song. It is the time it takes to soft-boil an egg or to walk to the end of a long street and back. Most of the important things that happened in the world that day took far longer than 200 seconds and were far easier to explain. But this particular calculation, performed by this particular machine, is one of the strangest events in the history of human technology, and almost nobody noticed it happen. There was no countdown, there was no live broadcast. There were a few engineers, mostly in their 30s, standing in a quiet laboratory, and one of them double-checked a number, and one of them probably went to make coffee, and the machine kept humming the way it had been humming all morning. The machine was called Sycamore. It was built by Google, and at its heart was a chip about the size of a coin, holding 53 of something called qubits. We will get to what a qubit is. For now, hold on to the number, 53. The chip was cooled to a temperature of about 20 thousandths of a degree above absolute zero, which is colder than the empty space between the stars, colder than the faint afterglow of the Big Bang itself. It sat inside a cylinder of copper and gold, suspended from the ceiling, wrapped in stages of refrigeration, each stage colder than the one above it. And on that October morning, the engineers gave it a problem to solve. The problem itself was deliberately strange. It was not a useful problem. It was not the kind of thing you would ask a computer to do because you wanted the answer. It was a problem chosen precisely because it is the kind of problem that classical computers, the ordinary kind, the kind in your phone and your laptop and the data centers that run the modern world, find almost impossible. The technical name for it is random circuit sampling. You can think of it, very loosely, as asking the machine to roll an enormously complicated set of dice and report exactly how those dice tend to land. For a quantum machine, this is a natural thing to do. For a classical machine, it is a nightmare, because the number of possibilities that have to be tracked grows beyond all reason. Sycamore did it in 200 seconds. Google's engineers then asked a reasonable follow-up question. How long would the most powerful ordinary computer on Earth take to do the same thing? At the time, the most powerful ordinary computer on Earth was a supercomputer called Summit, a machine that filled a room the size of 2 tennis courts, built by IBM, drawing enough electricity to power a small town. Google ran the numbers and published a figure. Summit, they said, would need approximately 10,000 years. 10,000 years. To put that against 200 seconds, you have to understand the size of the gap. 10,000 years ago, human beings had not yet invented writing. The wheel did not exist. The great cities of the ancient world were still thousands of years in the future. If you had started Summit on this calculation, at the dawn of human civilization, it would still be running today, and it would not be close to finished. Sycamore did it in less time than it takes to listen to the opening of this video. Now, this is the part of the story where honesty matters, because IBM did not let that figure stand. IBM is the company that built Summit, and IBM's engineers pushed back. They argued that Google had not been generous enough to the classical machine. With a cleverer algorithm, IBM said, and with enough hard disk storage to hold the intermediate steps, Summit could finish the same calculation in roughly 2.5 days. Not 10,000 years. 2.5 days. You might think that settles it. You might think that if one company says 10,000 years and the other says 2.5 days, then the whole thing was overblown, a marketing exercise, a quarrel between corporations. But look closer at what the quarrel was actually about. Google said 10,000 years. IBM, defending its own supercomputer, doing everything it possibly could to make the classical machine look good, said 2.5 days. And 200 seconds is still vastly smaller than 2.5 days. Even under IBM's most favourable accounting, even with every advantage handed to the ordinary computer, the quantum machine was still around 1,000 times faster. The two companies were not arguing about whether the gap existed. They were arguing about how many zeros were in it. And that is the first thing I want you to carry with you tonight because it is easy to miss. The dispute was about magnitude. It was never about existence. Both sides agreed that something had happened on that chip that an ordinary computer cannot easily follow. The machine works. That is the part that stays with me. Whatever you decide to believe about everything that follows in this video, and some of what follows is genuinely strange enough that serious physicists argue about it in public, you do not have to take any of it on faith. The machine works. It has been independently studied. It has been built again in other laboratories, by other people in larger and more capable forms. The strangeness is not a rumour. It is sitting in a refrigerated room, running. Let me describe that room to you, because we are going to come back to it at the very end of tonight's journey, and I want the picture to be in your mind early. Imagine a cylinder hanging from the ceiling of a laboratory. It is about the size of a chest freezer, but it does not look like a freezer. It looks like a chandelier built by someone who only worked in metal. Plates of copper and gold stacked one below the other, connected by bundles of wire and thin tubes, growing more delicate as they descend. Each plate is a stage of cooling. The top plate sits at around 50 degrees above absolute zero. The next, lower, sits at 4 degrees. Below that, 800 thousandths of a degree. Below that, 100 thousandths. And at the very bottom, on the smallest, coldest, most carefully isolated plate of all, sits the chip, the coin-sized piece of engineered matter, held at around 20 thousandths of a degree above the absolute floor of cold. There is no temperature like that anywhere in the natural universe. Deep space, the void between galaxies, is warmed to about 2.5 degrees above absolute zero by the leftover light of the Big Bang. The chip inside that cylinder is more than 100 times colder than the gap between the stars. Human beings made the coldest place we know of, and then we put a machine in it, and the machine does something that the ordinary universe of warm, ordinary matter cannot easily do. Why does it have to be so cold? Hold that question. It is a real question with a real answer, and the answer is part of the strangeness. But for now, just keep the image. A cylinder. Plates of gold and copper. A coin of matter colder than anything nature ever made. A faint, constant sound of pumps, and inside the coin, 53 qubits, doing something in 200 seconds that the ordinary world would need 10,000 years to imitate. Let me put you in that laboratory on the day it happened, because the scene is not what most people picture, and the gap between what they picture and what was real is itself worth feeling. There is no countdown, no banks of monitors with dramatic graphics, no team in matching jackets watching a screen. There is a room with ordinary fluorescent lighting and the low, continuous hum of the pulse tubes in the refrigerator, a sound a little like a distant heartbeat that never quite resolves into a rhythm. The chip has just finished its run. The result it has produced is on the surface almost comically unimpressive. A string of 53 ones and zeros, a single sample drawn from a probability pattern that no ordinary computer on Earth could reproduce in any human lifetime. An engineer, probably in their 30s, leans toward a screen and double-checks a number. Somewhere nearby, the coffee machine is running, because the coffee machine is always running. Nobody gasps. Nobody stands up. The most that happens in the moment itself is the quiet professional satisfaction of a long experiment behaving the way the theory said it would. And that is the thing that should stay with you about that morning. The universe had just been asked a question that no machine humanity ever built before could answer, and the answer came back in the time it takes to finish a cup of coffee, and the people in the room were calm because they had done their jobs well, and the strangeness of what they had done would take the rest of the world years to even begin to notice. The world mostly looked away. The story ran in the technology pages. It was filed under engineering, a milestone, a horse race between two big companies, the kind of thing that matters to investors and specialists and nobody else. And that filing, that decision to treat this as an engineering story, is the single most important mistake in how this whole subject is usually told. Because the arrival of a working quantum computer is not, at its core, an engineering story at all. It is a story about what reality is made of. And to see why, we have to leave the laboratory in Santa Barbara and travel back across the Atlantic Ocean and back more than 30 years to a quiet house in the English city of Oxford, where a man was sitting alone at a desk late at night, writing a paper that almost nobody would read. Part 2. The Man in the Oxford House. The man's name was David Deutsch, and to understand what he did, you have to understand the kind of person he was, and is, because he is still alive, still in Oxford, still working. David Deutsch does not fly on airplanes. He rarely leaves the city. For decades he has kept unusual hours, working through the night and sleeping through the day, in a house that became famous among the small community of people who knew him for its particular quality of stillness and clutter. He held no ordinary university position for much of his career, no department to run, no lectures to give, no committee meetings. He simply thought and wrote, supported by a loose arrangement with Oxford that left him almost entirely free. He is, by a wide margin, one of the most original physicists of the last 50 years, and he arranged his life so that he could follow a single thread of reasoning wherever it led, without anyone telling him to stop. Picture the house at night. The city of Oxford outside is asleep, the old stone colleges dark, the streets empty, the spires standing against a sky that, in a city, never quite goes fully black. Inside, one room has a lamp on. There is a desk, there are papers, there is a man who has decided that the most interesting thing he could possibly do with his finite life is to think, very carefully, about a question that most physicists had agreed, by unspoken consensus, not to think about too hard. He is still there tonight, in a sense. The house is real. The work continues. When you picture the origin of the idea at the centre of this video, do not picture a laboratory or a conference hall. Picture a single desk lamp, a city asleep, and a man following an argument into the dark. In 1985, in that house, David Deutsch wrote a paper. Its title was forbiddingly technical: Quantum Theory, the Church-Turing Principle, and the Universal Quantum Computer, and it appeared in a journal called the Proceedings of the Royal Society. It is now considered one of the founding documents of the entire field of quantum computing. The machine in Santa Barbara, the Sycamore chip, the cold cylinder of gold and copper, all of it traces back through a long chain of other people's work to the argument in that paper. But here is what almost nobody tells you about that paper. It was not, in Deutsch's own mind, primarily a paper about building a new kind of computer. Deutsch was not, first and foremost, an engineer dreaming of better machines. He was a physicist asking a question about the nature of reality, and the quantum computer was, for him, a consequence of the answer, almost a side effect. He worked out that a quantum computer should be possible because of what he already believed about the universe. The machine was the proof of the idea, not the goal of it. So what was the idea? To get there, I have to introduce you, gently, to the thing the whole video circles around, the qubit. We have been saying the word. Now let us slow down and actually look at it, because everything else depends on it. An ordinary computer, your phone, your laptop, the machine these words may be playing from, stores everything it knows in bits. A bit is the simplest possible piece of information. It is a switch. It is either on or off. We write those two states as 1 and 0. Every photograph, every song, every word of every book that has ever been digitized, every video on the internet is, at the deepest level, an enormous arrangement of these switches, each one definitely on or definitely off. That is the whole vocabulary of the classical world of computing. 1 or 0, on or off, this or that. A bit is always in one definite state, and you can always, in principle, walk up to it and ask which state it is in, and it will have an answer. A qubit is not like that. A qubit is also a switch, in a sense. It also has an on state and an off state, a 1 and a 0. But a qubit, while it is doing its work while nobody is looking at it, is not required to be definitely one or definitely the other. It can be in what physicists call a superposition, a state that is, in a way our everyday language is simply not built to describe, both possibilities held together at once, not rapidly flickering between them, not secretly one of them while pretending to be both, genuinely, mathematically both. described by a single quantum state that contains the 1 and the 0 woven together, each with a certain weight. Now, if you have 1 qubit, this is interesting but not yet overwhelming. 1 qubit holds a blend of 2 possibilities, the 1 and the 0. But qubits, when you bring them together, do not simply add, they multiply. 2 qubits together hold a blend of 4 possibilities at once. 3 qubits hold 8. 4 qubits hold 16. Every single qubit you add does not add to the count of possibilities, it doubles it. And doubling, repeated, is the most explosive kind of growth there is. This is where Deutsch's mind went sitting at that desk. He followed the doubling, and the doubling, followed far enough, leads somewhere that should make the floor feel unsteady under you. We are going to follow it ourselves, slowly and carefully in the next part of the journey, because it is the heart of the whole matter. But let me tell you in advance where the doubling took David Deutsch, so you know what we are walking toward. He concluded that when a quantum computer of even a modest size performs a calculation, the number of separate possibilities it is working through at the same time can become larger, vastly, absurdly larger, than the number of atoms in the entire observable universe, larger than everything, larger than every particle in every star in every galaxy that any telescope will ever see. And that left him with a question that he did not consider rhetorical. He considered it a real, physical question, demanding a real, physical answer. If a machine sitting on a table in Oxford or in Santa Barbara is genuinely working through more possibilities than there are atoms in the universe, then where is all of that happening? Where is the calculation taking place? It cannot be fitting inside the machine, because the machine is small. It cannot be fitting inside the universe we can see, because we just said the numbers are bigger than the universe we can see. Deutsch's answer, and it is the reason this video exists, was that the calculation is real, and it is physical, and it is happening, and if it does not fit inside the universe we can see, then the universe we can see is not the whole of what exists. The calculation, he argued, is distributed across many universes, across many parallel versions of reality, each with its own version of the machine, each working on a piece of the problem, the results flowing back together into the single answer that appears on the screen in front of us. He did not mean this poetically. He meant it as physics. He meant that the other universes are as real as this one, and that a quantum computer is the first machine human beings have ever built whose ordinary everyday operation reaches into them and uses them. That is the claim. That is the terrifying truth the title of this video is pointing at. Not that the machines are fast. That they're working, taken seriously, says the reality you can see is a single room in a house with an unknown number of other rooms, and we have built a device that opens the door. When Deutsch published that argument in 1985, the response from most of the physics community was not outrage. Outrage would have been a kind of attention. The response was something quieter and in its way harder. The paper was read by specialists, admired for its technical content, cited for its contribution to the theory of computation, and its central claim about parallel universes was, very largely, set aside, treated as the eccentric philosophical opinion of a brilliant man. The kind of thing you politely do not bring up. For a long time, that is where the idea sat, a claim in a paper, a position held seriously by a small number of physicists, and quietly declined by most of the rest. It might have stayed there forever, an interesting footnote, a road not taken. What changed everything was that the machines got built. The argument stopped being something you could only think about. It became something humming inside a cold cylinder in California. And so we have to do what David Deutsch did at that desk. We have to follow the doubling ourselves and see, with our own minds, where it goes. Part 3. The counting. I want you to do something with me now, and it does not require any mathematics beyond counting. It only requires patience and a willingness to keep going a little past the point where the numbers stop feeling real. That discomfort, that point where the numbers stop feeling real, that is not a failure of understanding. That is the understanding. That feeling is the thing this part of the journey is meant to give you. Imagine you are standing at the base of a quantum computer, not Sycamore with its 53 qubits. Imagine a slightly larger one, a machine with 300 qubits. 300 is not a fantastical number. It is not science fiction. Machines with far more than 300 physical components already exist, as we will see. 300 qubits is a near-future machine, a modest one, the kind that engineers speak about without lowering their voices. We're going to count the possibilities that a 300-qubit machine holds, and we count them the only way they can be counted, by doubling. 1 qubit, 2 possibilities. 2 qubits, 4. We add a qubit, we double the count. So let us start doubling, and let us not stop. 1, 2, 4, 8, 16. We have 5 qubits, 32, 64, 128, 256, 512. We have 10 qubits, and we are already past 500. Keep doubling. By the time we have counted out 20 qubits, the number of possibilities has passed 1 million. By 30 qubits, it has passed 1 billion. We are not even a tenth of the way to 300, and we have already left the millions and the billions behind. Keep going, do not stop. By the time we reach 50 qubits, roughly the size of the sycamore chip, the number of possibilities is more than a quadrillion. A 1 followed by 15 zeros. Already this is a number with no real feel to it. You cannot picture a quadrillion of anything. But we are only 1/6 of the way through our count. We have 250 qubits still to add, and every one of them doubles the total again. Let me give you some landmarks so you can feel the size of the country we're walking into. Keep doubling, and somewhere around the 80th or 90th qubit, the number of possibilities our machine is holding passes the number of grains of sand on every beach and in every desert on the entire planet Earth. Every grain, every beach, every desert. All of it counted is a smaller number than the possibilities inside a 90-qubit machine, and we are not even a third of the way to 300. Keep doubling. Somewhere past the 150th qubit, the number passes the count of every water molecule in every ocean on Earth. Think about that for a moment. The oceans are the largest single thing on the surface of our world. They are unimaginably vast quantities of water, and water is made of unimaginably tiny molecules, so the number of molecules in all the oceans together is a number of monstrous size. And a 150-qubit machine, half the size of the one we are counting, holds more possibilities than that. We are halfway, keep doubling, keep going. 200 qubits, 250, and finally 300. When you have finished, when you have doubled 300 times, you arrive at a number that, written out, looks like this. It is a 2 followed by 90 zeros. Written out it looks like this, a 2 and then 90 zeros marching across the page. That is the number of distinct possibilities a 300-qubit quantum computer holds in superposition while it works. Now let me give you the landmark that matters most, the one that is the whole reason we did this counting. Astronomers and physicists have estimated, as carefully as such a thing can be estimated, the total number of atoms in the observable universe. Not the galaxies, the atoms. Every atom in every grain of dust, every atom in every planet, every atom in every star, in every one of the hundreds of billions of galaxies that our telescopes can reach. The number they arrive at is, very roughly, a 1 followed by 80 zeros, a 1 followed by 80 zeros, that is everything we can see, a 2 followed by 90 zeros, that is the number of possibilities inside one modest quantum computer. Look at those two numbers next to each other. 80 zeros for the entire visible universe, 90 zeros for the machine. The difference is not small. The difference is itself a number with 10 zeros after it. The quantum computer holds something like 10 billion times more possibilities than there are atoms in everything we can see. So let yourself stand for a moment at the base of that machine and count it again, slowly, in your mind. You begin small, 1, 2, 4, 8. The numbers are friendly here, you can still hold them. 16, 32, 64. You keep doubling, and the doubling keeps its quiet rhythm. And somewhere in the gentle climb the numbers stop being friendly and start being landmarks. You pass the grains of sand on every shore of the world, and you do not stop. You pass the count of every molecule of water in every ocean, and you do not stop. You pass the stars, and then the atoms inside the stars, and then the atoms inside every star in every galaxy any telescope will ever find. And you do not stop because the machine has not stopped, because there are still qubits left to add, and each one doubles the total again. And here is the strange thing about that climb. There is no single step where it becomes impossible. Every individual doubling is small. Every individual doubling is just 2 times what came before, the most ordinary operation there is. The impossibility is not in any one step. It is in the patient accumulation of them. The way a feather laid on a feather laid on a feather will, with enough patience, outweigh a world. You're not doing anything difficult, you're only counting, and the counting, all by itself, has carried you out through the wall of everything that exists and set you down somewhere there is no name for. Holding a number the universe has no room to hold. Now stop and stand inside that fact and feel where it leaves you. The machine is real. We have established that. It is not a theory. It is a physical object, and it does physical work, and when it works, it is working through this monstrous, universe-exceeding number of possibilities. The possibilities are not a metaphor. They are not a loose way of describing the math. They are what the machine is actually doing. And here is the question David Deutsch refused to wave away, the question that should make the ground tilt very gently under your feet. If the machine is genuinely working through more possibilities than there are atoms in the visible universe, then where is the work being done? It is not being done inside the chip. The chip is a coin of matter. It has only so many atoms in it, and they are vastly, vastly too few. It is not being done in some hidden storage somewhere in the laboratory, because there is no storage in the laboratory, or on the Earth, or in the visible cosmos, large enough to hold a 2 followed by 90 zeros. Before we look at the answers, let me close one comfortable exit, because most people, hearing this for the first time, reach for it instinctively. The comfortable exit is to say, surely this is just a trick of the mathematics. Surely the possibilities are not a real, countable inventory of things. Surely they are just a way of writing the equations, a notation, the way an accountant's ledger has columns that do not correspond to physical objects. And if it were only notation, the discomfort would dissolve, and we could all go back to sleep. But here is why that exit does not quite open. The possibilities are not idle entries in a ledger. They interact. That is the whole point of a quantum computation, and it is the thing an ordinary metaphor cannot reach. Inside the machine, the vast set of possibilities do something to each other. They combine, they reinforce, they cancel, in a process physicists call interference. The wrong answers, the unhelpful paths, are arranged so that they cancel one another out, like waves meeting crest to trough and flattening. The right answer, the helpful path, is arranged so that its contributions reinforce, like waves meeting crest to crest and building. The single answer that finally appears is the survivor of that interference. And you cannot have interference between things that do not exist. A possibility that was never real cannot cancel another possibility. The cancellation is the proof that there was something there to cancel. The machine's output is, in effect, a receipt, and the receipt is itemized. So you have, really, only two ways to respond to this. The first way is to say, the possibilities are not real, they are just bookkeeping. Just a mathematical convenience, a way of organizing a calculation that is really, somehow, happening in a perfectly ordinary place by perfectly ordinary means. This is a respectable position, and we will give it its full due later tonight, because intellectual honesty demands it. But notice the price of it. To say the possibilities are not real, you have to explain why a machine that manipulates not real possibilities reliably outperforms every real computer on Earth. You have to explain why the bookkeeping wins. You have to explain how things that do not exist manage to interfere with one another and leave a precise, repeatable answer behind. That is not an easy bill to pay. The second way is the way Deutsch took. You say, the possibilities are real, the work is genuinely being done, and if there is no room for it in the universe we can see, then there is more universe than we can see. The calculation is spread across an immense number of parallel realities. The machine is not a faster computer. It is a kind of bridge. And every time it returns an answer, the answer is a signal that has come back from somewhere a telescope will never point. I am not yet asking you to choose. I am asking you to feel the size of the choice. Most of the questions a science video puts to you are small questions, comfortable questions, questions where any reasonable answer leaves your picture of reality basically intact. This is not one of those. Both available answers cost you something. One of them costs you the realness of what the machine plainly does. The other costs you the idea that the universe you can see is all the universe there is. And before you decide, before you can fairly decide, you should know that the man whose mathematics made all of this possible, the man who first wrote down the equations that say the universe should branch like this, did not live to see a single quantum computer switch on. He died believing he was right, with almost no one agreeing with him. His name was Hugh Everett, and his story is the saddest thing in this video, and we are going to tell it now. Part 4. Everett's Grave. In the autumn of 1957, a young man walked through the campus of Princeton University in New Jersey, carrying a typed document and handed it in. He was 27 years old. The document was his doctoral dissertation. His name was Hugh Everett III. Picture him on that walk. He is young and tired in the specific way that finishing a doctorate makes a person tired. He has been working under one of the most respected physicists in the world, a man named John Archibald Wheeler. And we will hear more about Wheeler later, because he is important to this story twice over. Everett does not know, as he carries those pages across campus, that he is holding one of the most consequential physics documents of the 20th century. He thinks probably that he is holding a finished obligation. He thinks he's about to be done. He's about to hand it to the typing pool, watch it become official, collect his degree and get on with his life. He has no idea that the mathematics in his hands will, 70 years later, be cited in the engineering documents of corporations worth more money than most of the nations on Earth. He has no idea that machines will be built, cold machines, in cold rooms, whose existence will be explained by serious people using the argument in those pages. He cannot know any of that. What he's about to find out instead, over the next few years, is that the world does not want his idea at all. Let me tell you what the idea was, because it is the foundation under everything. For 30 years before Everett, physicists had been living with a deep and genuinely embarrassing problem at the center of quantum mechanics. The mathematics of quantum theory is, in its undisturbed form, beautifully clear. It describes a system, a particle, an atom, a qubit, as a smooth blend of possibilities, all present together, evolving in a clean and predictable way. The 1 and the 0, woven together, just as we described. That is the math when nobody is looking. But then somebody looks. Somebody makes a measurement. And in that instant, the textbook said, something abrupt and inexplicable happens. The smooth blend of possibilities suddenly, violently collapses down to a single one. The particle, which had been a blend of here and there, snaps to here. The qubit, which had been a weave of 1 and 0, snaps to 1. All the other possibilities simply vanish. And the theory had no mechanism for this. No equation described the collapse. It was just asserted, bolted onto the side of the beautiful mathematics, because it seemed to be what happened. The official position, associated with the great physicist Niels Bohr and called the Copenhagen interpretation, essentially said, do not ask. The collapse happens when a measurement happens. What counts as a measurement? Do not ask. The math works, the predictions are right, do not ask what it means. Hugh Everett, 27 years old, asked. And his answer was as simple as it was shocking. He said, what if the collapse never happens? What if there is no special, magical, unexplained snapping down? What if the smooth mathematics is simply true all the time, for everything, with no exceptions, including for the measuring device, and including for the physicist doing the measuring? Follow what that means. If there is no collapse, then when a physicist measures a qubit that is a blend of 1 and 0, the blend does not snap to a single value. Instead, the blend spreads. The physicist becomes part of it. The universe now contains a version of events in which the physicist saw one, and equally real, a version in which the physicist saw 0. Both happen. Both are real. The world does not choose. The world branches into 2 histories, 2 copies, each complete, each containing a complete copy of that physicist, each unaware of the other. And it does not happen only in laboratories. Every quantum event, everywhere, all the time, and the universe is built out of quantum events, splits the world again. The branching is constant, silent, and unimaginably vast. Reality, in Everett's picture, is not a single thread. It is an endlessly dividing tree, and you're on one twig of it, and there are countless other twigs, every one as real as yours, holding versions of everything, including versions of you. That was the dissertation. That was the idea the young man carried across the Princeton campus in 1957. The physics establishment of the day did not embrace it. Niels Bohr was the most towering authority in the field, and the Copenhagen view was Bohr's view, and Everett's idea was, in the most direct possible way, a statement that the Copenhagen view was incomplete. Everett's own supervisor, John Wheeler, who admired the work, also revered Bohr, and worked hard to soften the dissertation, to file down its edges, to make it sound less like a challenge. Everett travelled to Copenhagen to discuss his idea with Bohr's circle directly. The visit did not go well. The reception was cold. The young man's great idea was essentially declined. And here is the part that gives this story its real weight. Hugh Everett did not spend the next decades fighting for his idea. He did not become the gadfly of physics conferences, the man who would not let it go. He did something quieter and sadder. He left. He walked away from academic physics almost entirely. He took his considerable mathematical brilliance to the United States defense industry, and he spent his career building mathematical models for nuclear war, calculating fallout patterns, calculating the optimal targeting of weapons, doing the cold arithmetic of mass death for the Pentagon. He was good at it. He made money. He bought a large house. He also drank, heavily and steadily for years. He smoked constantly. He grew heavier. He was, by the accounts of those who knew him, often distant, often difficult. A man with a formidable mind and a private weather system nobody could quite read. And on a morning in 1982, his teenage son found him. Hugh Everett III had died in his sleep, of a heart attack, on a couch in his own house. He was 51 years old. He had requested in advance what should be done with his remains. He asked to be cremated, and he asked that his ashes be thrown out with the household trash. And his family eventually honoured that request. The man who gave the world the idea of infinite branching realities asked for his own physical remains to be discarded like refuse, because in the universe as he understood it, it genuinely did not matter what happened to any one particular arrangement of atoms. The configuration that had been Hugh Everett was only ever one twig. He believed that completely. He believed it enough to write it into his own ending. And here I want to slow down, because the sorrow of this story did not end with Hugh Everett. It moved through the people who loved him. His daughter, Elizabeth, struggled for many years with her mental health. There is a line attributed to her from a diary that is almost unbearable to read once you know what her father believed. She wrote that she hoped to die so that she might find him again in a parallel universe. Years later, she took her own life, and she asked, in the note she left, that her remains be treated as her father's had been, discarded, so that she might, as she put it, arrive in the right parallel universe to be with him. The idea that the physicist had written down as cold mathematics had become, for his own child, a kind of terrible hope. Everett's son, Mark, lived. He became a musician. He leads a band called Eels, and he has spoken and written, over the years, with remarkable gentleness, about what it was to be the one left behind, the last surviving member of that small family carrying its story. I do not tell you this to be grim. I tell you because it is the human weight under everything else in this video, and it should not be skipped over to get back to the machines. The point is not that Hugh Everett was right. The machines may yet vindicate him completely, or they may not. The point is quieter and harder than that. The point is that an idea can be true, or close to true, and still cost the people who carry it almost everything, and that the man who gave the world the picture of infinite branching realities and every person who loved him lived and died inside the one branch where the idea brought them no comfort at all, only a long isolation, and not one of them lived long enough to see the day the cold machines began, every hour to behave as though he had been right. Because vindication did come. It came too late for him, and too late for everyone who loved him, but it came. Slowly, through the 1970s and after, a younger generation of physicists picked the dissertation back up. They found in it not an embarrassment but a kind of clean honesty, a version of quantum mechanics with the ugly, unexplained collapse simply removed, leaving only the beautiful mathematics, allowed at last to mean what it says. They gave the idea the name it carries today. They called it the many worlds interpretation. And then, decades further on, the engineers arrived, the builders of quantum computers, and they found that Everett's picture was not just philosophically tidy, it was useful. It was, for many of them, the most natural way to say out loud what their machines were doing. When David Deutsch argues that a quantum computer's calculation is spread across parallel realities, he's standing squarely on the dissertation that young man carried across Princeton in 1957. Every time one of those cold machines in its cold room returns an answer, it is, on this reading, a small confirmation of the idea that cost Hugh Everett his place in physics and gave his family nothing but a long sorrow. Somewhere in some branch he is still alive, If his own theory is right, and the machines, every day, behave as though it might be, then there is a version of events in which the young man's idea was embraced, in which Bohr nodded instead of frowning, in which Hugh Everett stayed in physics and grew old inside the field he transformed and watched, with his own eyes, the first quantum computer switch on. That branch, if his mathematics is correct, is as real as this one. We're simply not standing in it. We're standing in the branch where it went the other way, where the idea was right and the man was broken by it, and we are left to do the strange work of honouring him by taking his impossible idea seriously. So let us take it seriously. Let us leave the sad house behind, and the campus, and the year 1957, and let us go and look hard at the actual physics, at the experiments done with real equipment by living scientists that tell us the quantum strangeness Everett built his life around is not a story. It is a measured fact about the world, and it begins with a different physicist, an even more famous one, who was absolutely certain that all of this had to be wrong. Part 5. What Einstein got wrong. In 1935, Albert Einstein, working with two younger colleagues named Boris Podolsky and Nathan Rosen, published a short paper that was designed, very deliberately, to wound quantum mechanics. The three of them did not like where the theory was going, and they believed they had found its fatal flaw. The paper is known, after the initials of its three authors, as the EPR paper, and the flaw it claimed to expose has a name that has since become famous. Einstein called it, in a letter, spooky action at a distance. I'm going to try not to use that phrase much tonight because it has been repeated so many times that it has gone soft like a coin worn smooth. So let me describe the actual thing it points at, in plain language, because the actual thing is anything but soft. Quantum mechanics allows two particles to be joined in a particular way. The technical word is entangled. When two particles are entangled, they are described, and this is the crucial part, by a single shared quantum state. Not two states that happen to match. One state, covering both particles together, even after the particles have been carried far apart. You can entangle two particles in a laboratory, and then send one of them to the other side of a city, the other side of a continent, in principle the other side of the galaxy. They remain, in the mathematics, one connected thing, and here is what that connection does. Each of the two particles, on its own, has some property that is genuinely undecided, a blend of possibilities, the way a qubit is a blend of 1 and 0. Suppose the property is something physicists call spin, and suppose it can come out up or down. Before anyone looks, neither particle is up and neither is down, each is the blend. But the two are entangled in such a way that whatever one of them turns out to be, the other must turn out to be the opposite. If one is found to be up, the other will be found to be down. Always, without exception, no matter how far apart they have been carried. Now here is the knife. You take your particle, here, and you measure it, and it comes out up. At that instant you know, with total certainty, that the distant particle, which nobody has touched, which may be light years away, will be down. The question Einstein drove at is brutally simple. How does the distant particle know? There were, broadly, two possible answers, and Einstein was certain he knew which one a sane universe would choose. The first answer, Einstein's answer, is the comfortable one. It says the particles were never really undecided at all. It says that from the moment they were created and separated, each one was secretly carrying a definite, settled instruction. This one is up, that one is down, and the quantum blend was never the deep truth, only our ignorance of the hidden instruction. On this view, measuring your particle does not change the distant one at all. It simply reveals what was already fixed, the way opening one of a pair of sealed envelopes tells you what is in the other. No spookiness, no action at a distance, just hidden information, set in advance. Physicists call this idea local hidden variables, and Einstein believed deeply that it had to be the truth, because the alternative offended everything his instincts told him about how a reasonable universe behaves. The second answer is the quantum one, and it is the one Einstein could not stomach. It says the particles really were undecided, genuinely, completely, both possibilities at once, right up until the moment of measurement, and it says that measuring your particle here genuinely does reach out and settle the distant one, instantly, across any distance, with no signal travelling between them, because the two were never really two separate things. They were one connected object the whole time, and you cannot do something to half of a connected object without doing it to the whole. For 30 years, this argument could not be settled. It looked for 30 years like a matter of philosophy, of taste, of which picture of the world a physicist found more comfortable, and you were free to side with Einstein, and many did, because siding with Einstein is usually a safe bet. Then, in 1964, a quiet Irish physicist named John Stuart Bell did something that changed the question forever. Bell found a way to make the disagreement testable. He proved a mathematical result, now called Bell's theorem, or Bell's inequality, that did something almost no one had thought possible. He showed that the two pictures, Einstein's hidden instructions and the quantum connection, do not merely sound different. They predict different numbers. If you set up the right experiment, measuring entangled particles many times over, at angles chosen just so, then a universe running on Einstein's hidden instructions can only produce results within a certain mathematical limit. And a universe running on the genuine quantum connection can break straight through that limit. Bell handed physics a referee. The philosophical argument had become an experiment. All someone had to do was build it. It was not easy to build. It took years, and better technology, and the particular determination of a handful of experimenters. But through the 1970s and into the early 1980s, the experiments were done, and the most famous and decisive of the early ones was carried out in 1982, near Paris, by a French physicist named Alain Aspect, at an institution called the Institut d'Optique. Picture Aspect's experiment because it is one of the most important experiments ever performed, and it is strangely beautiful. A source at the centre of the room produces pairs of entangled photons, pairs of particles of light born together, sharing a single quantum state. The two photons of each pair fly off in opposite directions down the room toward two distant detectors, and as each photon races toward its detector, the apparatus very rapidly switches the angle at which that photon will be measured, switches it so fast, so late, that there is no time for any ordinary signal, travelling at the speed of light, to cross from one side of the room to the other and quietly coordinate the result. Each side decides how to measure independently at the last possible instant, and then the two results are compared. Bell's theorem said, if Einstein is right, the correlations between the two sides must stay within the limit. Aspect ran the experiment and gathered the data, and the data broke the limit, cleanly, decisively. The universe came down, hard, on the side of the genuine quantum connection. Einstein's comfortable hidden instructions are not how the world works. Now, for many years afterward, careful physicists noted that the early experiments, aspects included, still had small technical gaps, what they called loopholes, tiny cracks through which a very stubborn defender of Einstein might still try to escape. Maybe the detectors missed too many particles. Maybe the angle switching was not quite fast enough or quite random enough. Closing every one of those loopholes all at once in a single experiment took another 3 decades of work. And in 2015, a team in the Netherlands, at Delft University of Technology, led by a physicist named Ronald Henson, did exactly that. They performed a Bell test with every known loophole closed simultaneously. The result held. The quantum connection is real. It is not hidden instructions. It is not our ignorance. It is a genuine feature of the world. And in 2022, the Nobel Prize in Physics was awarded to Alain Aspect, to an American physicist named John Clauser, who had done crucial early work, and to the Austrian physicist Anton Zeilinger, whose group pushed entanglement experiments to extraordinary lengths. The official citation honoured them for experiments with entangled photons that established the violation of Bell's inequalities and pioneered quantum information science. The highest institutional authority in physics had spoken. Einstein was wrong about this. The spookiness is real. I want to be careful and precise here, because this is exactly the kind of place where overstatement creeps in. The entanglement connection, real as it is, does not let you send a message faster than light. It does not because the outcome on each side taken by itself is pure randomness. Up, down, down, up, with no pattern you can control. The connection only shows itself afterward, when the two lists of results are brought together and compared. So there is no telephone to other places, no faster than light signal, no violation of the cosmic speed limit. We will not pretend otherwise. But what there is strange enough without exaggeration. The world is built so that two particles, once joined, stay one connected thing across any gulf of distance. And reality, at its root, does not honour the tidy separateness that every one of our instincts insists on. I want to pause on John Bell himself for a moment, because his part in this is easy to rush past and it deserves better. Bell was not a celebrated revolutionary working at the glamorous centre of physics. He was an Irish physicist, the son of a working family in Belfast, and for most of his career his main job was the practical, demanding work of accelerator physics at the great European laboratory near Geneva. The theorem that carries his name, the result that turned a 30-year philosophical stalemate into a decidable experiment, was something he worked out, in his own words, almost as a hobby on the side, because the question would not leave him alone. And here is the detail that gives it weight. Bell has said that in his own instincts he was somewhat on Einstein's side. He found the quantum connection uncomfortable. He half hoped that his theorem would open a path for the hidden instruction picture to win. It did the opposite. Bell built the referee fairly with no thumb on the scale, and the referee ruled against the very picture its own author found most comfortable. There is a quiet heroism in that, a man constructing with great care the single test most likely to overturn his own preference, and then accepting the verdict when it arrived. Bell died in 1990 suddenly, of a stroke, at the age of 62. It is widely believed that had he lived even a few years longer, he would have shared in a Nobel Prize. The work that finally won that prize in 2022 was nothing other than the experimental confirmation of his theorem, the proof that the referee he had built was telling the truth all along. And now connect all of this back to the cold machine in the cold room, because this is why we took the long journey through Einstein and Bell and aspect. Entanglement is not a curiosity. Entanglement is the fuel. A quantum computer does not just hold its qubits in superposition, each one a private blend of 1 and 0. It entangles them, joins them into a single shared quantum state, so that the whole array of qubits becomes one connected object, far richer than the sum of its separate parts. That web of entanglement, that refusal of the qubits to remain separate things, is the resource the machine spends to do what no classical computer can follow. When Sycamore ran for 200 seconds, it was running on the very connection that Einstein was sure could not be real, and that Bell made testable, and that Aspect and the others proved, with photons and detectors and the patient closing of every loophole, to be a true and permanent fact of the universe we live in. So the strangeness is not coming from nowhere. It rests on some of the most carefully verified physics human beings have ever done, and the deeper we go into what that strangeness means, the stranger it gets. Because the next physicist we have to meet did not think the universe was made of particles or of energy or of matter at all. He thought it was made of information, and if he was right, then a quantum computer is not just using reality, it is reaching into the floor of it. Part 6. Wheeler's Universe. We have met John Archibald Wheeler once already tonight in passing. He was the supervisor who admired Hugh Everett's dissertation, and also helped to soften it. But Wheeler deserves to step forward into the centre of the story now, in his own right, because near the end of a very long life he reached a conclusion so strange and so simple that it reframes everything we have said so far. Wheeler was, by any measure, one of the great physicists of the 20th century. He worked at the deepest levels of the field for decades. He helped develop the theory of nuclear fission. He was the one who popularized the term black hole. He taught and shaped generations of physicists. He was not a man on the fringe. He was about as close to the establishment heart of physics as a person can stand. And it was from that position, with nothing left to prove, that the old Wheeler started saying something that sounded at first like a riddle. He put it in a short, strange phrase, it from bit. Here is what the riddle means. We naturally assume that the universe is fundamentally made of stuff, matter, particles, energy, the its, the things. And we assume that information is something secondary, something that comes along afterward, a description of the stuff, a label we attach to the things, useful but not fundamental. The stuff is real. The information about the stuff is just an account of it. Wheeler, late in his life, came to believe that this had it exactly backwards. It from bit means the it comes from the bit. The thing comes from the information. In Wheeler's mature view, information is not the description of reality. Information is the foundation of reality, and the particles, the matter, the solid-seeming world All of it emerges out of information, the way a sculpture emerges out of stone. Every particle, every field, every force, Wheeler said, derives its very existence from answers to yes or no questions. Did the photon go through the left slit or the right? Yes or no? Is the spin up or down? Yes or no? Is the particle here or not here? Yes or no? The universe, at its root, in Wheeler's picture, is the accumulated answers to an unimaginable number of such questions. And the questions, the bits, the yeses and nos, are what is truly fundamental. The stuff is the pattern the answers make. When Wheeler first said this kind of thing, it could be waved away as the poetry of a grand old man, a metaphor, the sort of thing brilliant physicists are allowed to muse about once they are too senior to be told off for it. But it is not only poetry, and the reason it is not only poetry is a hard, specific, experimental result that ties information directly to the physical world. That result is called Landauer's principle, and you should know it, because it is the moment the riddle grows teeth. In 1961, a physicist named Rolf Landauer, working at IBM, asked a question that sounds like it belongs to philosophy but turned out to belong to physics. He asked, does information have a physical cost? Specifically, when a computer erases a bit of information, when it takes a switch that was definitely on or definitely off and wipes it back to a blank default state, does that act of erasure cost anything in the physical currency of the universe, which is energy? Landauer proved that it does. He showed that erasing a single bit of information must release a minimum, unavoidable amount of heat into the surroundings. There is a precise flaw to it, a tiny number of joules, set by the temperature and by one of the fundamental constants of nature. You cannot erase information for free. The universe charges you in heat every single time. Erasing information is not an abstract act. It is a physical event, with a physical price, and the price is thermodynamic and real. For a long time this was a theoretical result, elegant, widely believed, but not directly seen. Then, in 2012, a team of physicists published an experiment in the journal Nature, in which they built a tiny system, isolated a single bit of information, erased it, and measured the heat that came out. The heat was there. It matched Landauer's prediction. The experiment confirmed directly in the laboratory that information is physical, that a bit is not a ghost, not a mere idea, but a thing entangled with the energy and the heat of the real world. Now let Wheeler and Landauer stand together and feel what they say as one statement. If information has a real, physical, thermodynamic cost, if erasing a bit genuinely releases heat, then information is not floating above the physical world as a description of it. Information is woven into the physical world, as real as energy, as real as heat. And if Wheeler is right that information is not just woven in, but is the foundation, the thing from which the its emerge, then the deepest layer of reality, the bedrock under the particles and the forces, is informational. The universe at the bottom is something closer to a vast computation than to a vast lump of stuff. And now follow that thought somewhere quiet and close, because it leads, with no detours, straight to you. If information is physical, if erasing a bit genuinely costs heat, as Landauer proved and the laboratory confirmed, then think about what thinking is. Thinking is the constant writing and rewriting and erasing of information. A memory forming is information being written. A memory fading is information being erased. Every moment of awareness, every shift of attention, every thought rising and giving way to the next thought is information in motion. And information in motion, we now know, is a physical process with a physical price paid in heat. Which means this: every thought you have ever had has cost the universe something. Every memory you hold and every memory you have lost released a small, real, measurable quantity of heat into the world as it formed or faded. You've been doing it your whole life. You're doing it right now, listening to this sentence. The understanding of these words is information being arranged inside you, and the arranging is warm. Sit with where that leaves you. The chair beneath you, the air moving in and out of your lungs, the light in the room, and the very thought you are thinking as you hear this. All of it is the same kind of thing. All of it is information, arranged, shedding warmth as it changes. And if that is so, then the wall this video has quietly leaned on all night. The machine over there, in its cold room. You over here, listening, separate, safe. That wall was never really there. You're not an outside observer of the informational universe, watching it through glass. You're a piece of it. The quantum computer in its refrigerated chamber and the mind that is following this voice are not two different categories of thing. They are the same kind of thing. One is simply kept very cold, and the other is kept warm, and warm is the temperature at which a piece of the universe can sit in the dark and wonder about itself. And this is why a quantum computer stops being an ordinary machine the moment you take Wheeler seriously. An ordinary computer shuffles information around on top of reality. It is a tool that sits in the world and moves bits about, the way a loom sits in a room and moves thread. But if reality is made of information at its foundation, then a machine built to manipulate information at the most fundamental physical level is not sitting on top of reality and moving its surface around. It is reaching down into the floor. It is operating on the substrate. It is not weaving cloth in a room. It is, in some small and carefully controlled way, doing the same kind of thing the universe itself does to exist. We have now seen the quantum computer through two lenses, and they do not contradict each other. They stack. Through Deutsch's lens, the machine's calculation is too large for one universe, and so it must be reaching across many. Through Wheeler's lens, the machine is manipulating the informational bedrock from which all the universes, all the branches, are themselves made. Hold both at once, a device that reaches across realities, operating on the layer of pure information beneath them all. There is one more lens, and it is the strangest of the three because it does not talk about information or about parallel branches in the abstract. It talks about the shape of space itself, and it suggests that the threads of entanglement humming inside every quantum computer are not connections through space at all. They are tiny tunnels in it. Part 7. The thread between particles. In the year 2013, two physicists published a paper with a title that sounds almost gentle, Cool Horizons for Entangled Black Holes. And inside that paper was an idea so audacious that, more than a decade later, physicists are still arguing about exactly how far to take it. The two physicists were Juan Maldacena, one of the most influential theorists alive, and Leonard Susskind, a founding figure in string theory and one of the deepest thinkers about the nature of space. And the idea they proposed has come to be known by a short equation that is really more of a slogan, ER equals EPR. We need to unpack both halves of that slogan, because each half is a piece of physics with its own history. Start with the right-hand side, EPR. You already know it. EPR is Einstein, Podolsky and Rosen, the three authors of that 1935 paper, the one that tried to wound quantum mechanics. EPR, in the slogan, stands for entanglement, the genuine quantum connection between two particles that we spent the whole of Part 5 establishing as real. Now the left-hand side, ER. ER stands for Einstein and Rosen again, but a different paper, also from 1935, the same remarkable year. In that other paper, Einstein and Rosen were studying the equations of general relativity, Einstein's theory of gravity, the theory that describes space and time as a flexible fabric that bends around matter. And they found, hidden inside those equations, a strange possibility. The equations seem to allow for a kind of shortcut, a bridge, connecting two separate distant regions of space through a tunnel that does not run through the ordinary space between them. Physicists later gave this shortcut a more famous name. They called it a wormhole. The technical term, the original term, is the Einstein-Rosen bridge. That is the ER. So now look at the slogan again. ER equals EPR. On the left, wormholes, tunnels through the fabric of space, born from the theory of gravity. On the right, entanglement, the quantum connection between distant particles born from quantum mechanics. Maldacena and Susskind proposed that these two things, which come from two completely different and famously incompatible parts of physics, are not two things at all, they are one thing, seen from two directions. They proposed that when two particles are entangled, they are, quite literally, connected by a wormhole, a microscopic, unimaginably tiny tunnel through the geometry of space itself. Let that settle, because it is a genuinely staggering claim. It says that the connection between two entangled particles is not some ghostly, abstract, non-physical link. It says the connection has a shape. It is geometry. It is a feature of the fabric of space, a tiny pinch or thread folded into the structure of reality, joining two points that look, From the outside, hopelessly far apart. Now, I have to be honest with you about the status of this idea, because honesty is the whole spirit of this channel, and ER equals EPR is not settled physics in the way that Bell's theorem is settled physics. Bell's theorem has been confirmed in the laboratory, loophole by loophole, with the highest honour in physics awarded for it. ER equals EPR is, as of right now, a conjecture, a profound, serious, widely studied conjecture, proposed by two of the most respected theorists alive, explored in hundreds of follow-up papers, and genuinely believed by many physicists to be pointing at something true. But it has not been proven, and the wormholes it speaks of, if they are real, are far too small and too non-traversable for anyone ever to crawl through or send a signal down. So hold this part of tonight's journey a little more lightly than the rest. This is the frontier. This is physics still being argued, but here is why it belongs in this video, even as a conjecture. If ER equals EPR is right, even roughly right, then look again at what a quantum computer is. A quantum computer, we have said, runs on entanglement. It works by weaving its qubits into a dense web of entangled connections, so that the whole array becomes a single connected object. That web of entanglement is the engine, and if every one of those entanglement links is, at the deepest level, a tiny wormhole, a thread of folded geometry, then a quantum computer, while it runs, is not merely shuffling abstract information. It is humming with billions upon billions of microscopic threads sewn through the fabric of space. It is, in the most literal sense the conjecture allows, an object that manipulates the geometry of space-time. Close your eyes, if they are not already closed, and hold this picture for a moment. Imagine two particles somewhere that once touched, that were created together side by side in a single event, and then flew apart. One of them drifts to the table in front of you. The other travels for 1,000 years and comes to rest on the far side of the galaxy. By the older instincts, the instincts Einstein trusted, those two particles now share nothing at all. The distance between them is total, and whatever happens to one can have nothing to do with the other. But by the picture Maldacena and Susskind drew, the two particles are still joined, not by a signal, not by anything passing between them. They are joined by a thread, a tunnel, impossibly thin, folded into the fabric of space itself, connecting the particle on your table to the particle a galaxy away. You could never crawl through that thread. You could never send so much as a whisper down it. But it is there. It is not a metaphor, and it is not a wire. It is the shape of space, bending quietly around the memory of a moment when those two particles were one thing. And now widen the picture. Every quantum computer running on Earth tonight is humming with billions upon billions of these threads. Every entangled pair inside it is one more stitch. The cold chip in its cold room is not calculating exactly. It is sewing, drawing thread after thread through the geometry of the world, building, out of pure connection, a fabric underneath the fabric you call distance. We have now built up the full strange picture, 3 lenses deep, and I want to gather it into a single image before we turn, in the next part, to something far more concrete and far more urgent. Through Deutsch's lens, the quantum computer's calculation is too large for one universe, and so its work is spread across countless parallel branches of reality. Through Wheeler's lens, the machine operates on information, and information is the bedrock from which all those branches are themselves built. And now, through Maldacena and Susskind's lens, the entanglement the machine runs on may be the very geometry of space folded into threads. Put the 3 together and the quantum computer becomes something almost impossible to hold steady in the mind, a device that reaches across realities, operating on the informational floor beneath them by sewing tiny tunnels through the shape of space. If the video stopped here, you might reasonably say, this is beautiful, and it is unsettling, but it is also abstract. It is happening in cold rooms, in a handful of laboratories far from my life. What does it have to do with me, tonight, lying here listening? So let us bring it close. Let us leave the frontier of geometry and wormholes and talk about something that touches your bank account, your messages, your medical records, and very possibly the security of the nation you're listening from. Because the same machine that may be sewing threads through space-time is also, on a more practical level, a key, and there are locks all over your life that it is being built to open. Part 8. The Lock and the Key. Almost everything you do that matters, in the digital part of your life, is protected by a single quiet idea. The idea is this: some mathematical problems are easy to do in one direction, and brutally, impossibly hard to do in reverse. Here is the specific problem that holds up much of the modern world. Take two very large prime numbers divisible only by themselves and 1. Multiply them together. That is easy. A child with enough patience could do it. A computer does it instantly. You get a very large result. Now hand that large result to someone else and ask them to work backwards, to find the two original prime numbers you multiplied. That reverse task, called factoring, is, for large enough numbers, effectively impossible for any ordinary computer. Not hard, not slow, effectively impossible. It would take the fastest classical machines on Earth longer than the age of the universe to crack a number of the size routinely used. That asymmetry, easy forward, impossible backward, is the lock. It is the foundation of a system called RSA encryption. An RSA and its relatives are what stand between your private life and anyone who wants to read it. When you see the little padlock in a web browser, when your bank moves your money, when a hospital stores your records, when a government transmits a secret, when a message app promises that only you and the person you are talking to can read what passes between you, underneath all of it, very often, is that same wager. The wager that nobody can factor the big number. The wager that the reverse problem is a wall. In 1994, a mathematician named Peter Shaw took that wall and showed where the door was. Shaw was working at Bell Labs, and he discovered an algorithm, precise procedure, that factors large numbers efficiently, quickly, tractably. There was just one condition attached to Shaw's algorithm. It does not run on an ordinary computer. It runs only on a quantum computer. Shaw proved in 1994 that a sufficiently large and reliable quantum computer would slice straight through RSA encryption, would take the impossible reverse problem, the wall the whole digital world leans on, and make it easy. In 1994, this was a beautiful and almost entirely theoretical result, because in 1994 there were no quantum computers, there was no Sycamore, there was no cold cylinder of gold and copper. Shaw had designed a key for a machine that did not exist, and so, for years, his results sat in the same comfortable category as Deutsch's parallel universes, brilliant, admired, and safely far away. It is not far away anymore, and the institutions whose job it is to think about exactly this have made their assessment very clear, not in words, but in actions. And the actions are worth reading closely because they tell you what the experts genuinely believe. In 2016, the United States National Institute of Standards and Technology, NIST, the federal body responsible for, among many other things, the encryption standards the country relies on, launched a global competition. The goal was to find and standardize a new generation of encryption methods, post-quantum encryption, methods built on mathematical problems that even a large quantum computer running Shaw's algorithm could not break. 82 teams of cryptographers from 25 countries submitted candidate methods. The submissions were attacked, tested, broken, refined, narrowed for 8 years. And in August of 2024, NIST published the finished standards, a small set of new algorithms with names like Crystal's Kyber and Crystal's dilithium, now formally recommended to replace the encryption that Shaw's algorithm threatens. Stop and weigh what that sequence of events actually means. Governments do not run 8-year global competitions and issue binding national standards and begin the slow, expensive process of re-encrypting the digital infrastructure of an entire country in response to a threat they consider imaginary or distant. You do not rebuild the locks on every door in the country because of a burglar who might, hypothetically, someday possibly exist. The 8-year timeline and the binding standards are a signal, and the signal reads, "The people with access to the real, classified assessments of how fast quantum hardware is advancing do not treat the arrival of a code-breaking quantum computer as a question of whether. They treat it as a question of when." And there is a second piece of this, and it is the coldest piece, and it is the reason the threat reaches backward in time. It is a strategy with a plain and chilling name: harvest now, decrypt later. Here is how it works. An adversary, a nation, an intelligence agency, any sufficiently resourced organization, does not need to wait for the code-breaking quantum computer to exist before it begins. It can begin today. It can intercept and copy enormous volumes of encrypted traffic right now. Your messages, financial records, state communications, diplomatic cables, all of it scrambled, all of it currently unreadable. And it can simply store that scrambled data, warehouse it, keep it on disk, patiently, for years. The data is gibberish today, but the day a large enough quantum computer switches on, every encrypted thing in that warehouse, going back years, can be fed through Shor's algorithm and read, which means the secrets you send today are only as safe as the distance to that machine. Anything you encrypt now that still needs to be secret in 10 years, or 15, or 20, a medical history, a state secret, the architecture of a defense system, the identity of a source, is potentially already sitting in a warehouse, already captured, already waiting. Written out, the number of encrypted messages currently flowing across the world every day looks like this. An unthinkable cascade of zeros, the entire encrypted traffic of a civilization. In part 3, a number that size was a wonder. We counted our way past the atoms of the universe and felt awe. This number, the same monstrous size, is not a wonder. It is a vault, and it is a vault that a future machine is being built to open. How far away is that machine? Here the honesty of this channel matters again, because the answer is genuinely uncertain, and anyone who gives you a confident date is selling something. The quantum computers that exist today cannot run Shor's algorithm against real-world encryption. They are not nearly large enough, or nearly reliable enough. The estimates for what it would take vary, but they cluster in a sobering range. Breaking the kind of RSA encryption in common use would likely require a quantum computer with somewhere between 1 million and several million high-quality error-corrected components working in concert, and one careful and widely cited study put the figure at around 20 million of the noisier kind of qubit, running for roughly 8 hours to factor a single large key. Today's machines have hundreds of qubits. Hundreds, not millions. So there is a gap, and the gap is real, and it may be wide, but remember what kind of growth we are dealing with. We are not dealing with steady linear improvement. We are dealing with a field whose central quantity has been doubling and doubling and doubling. We watched, in part 3, what doubling does, how it walks you, in a few dozen patient steps, from a handful to a number larger than the universe. A gap that looks like a canyon when the growth is linear can be crossed alarmingly fast when the growth is exponential. That is precisely why the institutions are not waiting. They have seen the shape of the curve, and it is not only an American story. On the 16th of August 2016, China launched a satellite. Its name was Micius, after an ancient Chinese philosopher, and it was the first quantum communication satellite ever placed in orbit. Micius was built to do something that sounds, again, like science fiction, and is simply true. It distributes entangled particles of light from orbit to the ground, sending the 2 photons of an entangled pair down to 2 separate ground stations, hundreds of kilometers apart, so that those distant stations share a genuine quantum connection. That connection can be used to create encryption keys protected not by the difficulty of a math problem, but by the laws of quantum physics themselves. Keys that, by their very nature, cannot be secretly copied, because the act of intercepting a quantum particle disturbs it and leaves a fingerprint. In June of 2017, the Micius team distributed entanglement between 2 ground stations more than 1,200 kilometers apart, and in September of that same year, they used the satellite to hold the first intercontinental quantum-encrypted video call between Beijing and Vienna, 2 cities 7,600 kilometers apart. A call that lasted 75 minutes, its security underwritten by the strange connection Einstein was certain could not be real. Picture that satellite for a moment, because it is one of the quietest and most beautiful machines in this whole story. It is night over the high country of northern China. The air on the mountaintop is thin and very cold, the kind of cold that is clean rather than cruel, and the sky above is the deep, uncrowded black you only ever see far from cities. There is an observatory there, and inside its dome a telescope is moving, slowly, steadily, with great patience, tilting to follow a single point of light crossing the stars. The point of light is Micius. It is more than 500 kilometers overhead, and it is not drifting. It is racing, crossing the sky at something like 7.5 kilometers every second, so that the whole pass, horizon to horizon, lasts only a few minutes. And in those few minutes, the satellite is doing something that ought to be impossible and is simply quietly real. It is sending down particles of light, photons, in entangled pairs, raining them out of orbit toward the waiting telescope. You cannot see this rain. No one can. It is far too faint, far too sparse, each photon a single fragile messenger. But the telescope can catch it, photon by photon, and each caught photon carries with it a thread of that genuine quantum connection, stretched now from space to the ground. There is no sound to any of it. There is only the cold air and the slow turning of the dome, and a machine in orbit letting an invisible rain fall very gently onto a mountain. You do not need to follow the physics to feel the calm of it. A satellite, a telescope, a thread of light, and the patient dark. So this is the practical face of the machine. Not parallel universes, not wormholes, locks and keys, satellites and warehouses, the quiet rebuilding of the world's encryption against a clock that nobody can read precisely, but that everyone serious agrees is running. The same device that may reach across realities is, in this nearer and harder light, a key being slowly cut for every lock you depend on. And it is about to take one more step, a step that happened recently, that changed the field's sense of what is possible, and that carried us, almost without anyone noticing, across a line we may not be able to step back over. Part 9. The Willow Moment. For decades there was a powerful and entirely reasonable argument that practical quantum computers would never work at all. It is worth understanding that argument, because the recent history of the field is the story of that argument being overturned, and the overturning is itself one of the strangest things in tonight's journey. The argument went like this. A qubit, holding its delicate superposition of 1 and 0, is exquisitely fragile. Almost anything will ruin it. A stray flicker of heat, a faint pulse of electromagnetic interference, a tiny vibration, the smallest unwanted nudge from the outside world. Any of these will cause the qubit to lose its quantum character, to decohere, to slump back into being an ordinary, definite, classical thing. And decoherence happens fast. Left exposed, a qubit holds its quantum state for only millionths of a second before the world rubs it away. This is the reason. Finally, here is the answer to the question I asked you to hold in part 1. This is the reason the chip must be kept colder than the space between the stars. The cold is not a preference. The cold is a desperate brute force attempt to quiet the universe enough that the qubits can think before they forget. Now scale that fragility up. A useful quantum computer does not need 50 fragile qubits. It needs thousands, then millions, all holding their quantum states together, all entangled, all staying coherent long enough to finish a long calculation. And the worry, the argument that said this would never work, was that errors would multiply faster than you could ever correct them. Every qubit you add is another thing that can break. Add enough qubits, the argument went, and you are not building a more powerful machine. You are building a machine that fails more often, until it drowns in its own errors. The fragility on this view was not a bug to be fixed. It was a wall, a permanent ceiling on the whole enterprise. In 1995, Peter Shaw, the same Shaw, and others began to fight back against that wall with an idea called quantum error correction. The idea, in spirit, is this. Do not try to make a single perfect qubit, because you cannot. Instead, take many imperfect, fragile physical qubits and weave them together cleverly so that they jointly store a single, much more robust unit of quantum information, a logical qubit. The logical qubit is the real workhorse. It is spread across many physical qubits, so that if any one of them slips, the others hold the information steady and the error can be detected and undone before it spreads. It is a little like spelling an important word across many voices in a choir, so that if one singer falters, the word is still unmistakable. There was a beautiful piece of theory attached to this, called the threshold theorem. It said that if you could make your individual physical qubits just good enough, better than a certain quality threshold, then error correction would not just help, it would win decisively. Below the threshold, adding more physical qubits to each logical qubit would make the logical qubit cleaner, not dirtier. The errors would fall away exponentially. The wall would come down. For years, that threshold sat there as a promise, proven on paper, never demonstrated in metal. Getting real physical qubits good enough and wiring enough of them together, and showing that the error rate actually fell as you scaled up, remained out of reach. It was the central open question of the field. Beautiful theory, no proof in the world. In December of 2024, Google answered it. They announced a new chip, and the chip had a name: Willow. Willow held about 105 qubits, not a dramatic jump in raw count. The raw count was not the point. The point was what Willow demonstrated. Google arranged Willow's qubits into error-correcting patterns of increasing size. A small grid, a larger one still, and they measured the error rate of the protected logical qubit at each size. And for the first time, clearly and convincingly, the error rate went the right way. As they made the error-correcting grid larger, as they spent more physical qubits to protect each logical qubit, the logical qubit got better. The errors fell exponentially, exactly as the threshold theorem had promised 3 decades earlier. Google had crossed below the threshold. They had demonstrated in a real machine that quantum error correction works at scale. I want you to feel how strange that reversal is, because it is easy to file it as just another engineering headline. For most of the history of this field, fragility was the enemy, and scale was the danger. More qubits meant more failure. Willow inverted that. After Willow, within the error-corrected regime, more qubits means more stability. The thing that was supposed to be the permanent ceiling became, instead, the staircase. The wall everyone had spent 30 years warning about turned out to be a door, and the door was unlocked, and behind it was the path to machines of a size that genuinely could, one day, run Shor's algorithm against the locks of the world. And the field did not pause to admire Willow. It moved. In the time since, the major players have pressed forward hard. The other giant of the field, IBM, has laid out an unusually specific public roadmap. Late in 2025, IBM unveiled a processor called Nighthawk, built on a new architecture, and stated plainly that it expects to reach verifiable quantum advantage, a quantum machine doing something genuinely useful that no classical machine can match, by the end of 2026. And IBM has named its destination beyond that, a large-scale, fault-tolerant quantum computer called Starling, with around 200 reliable logical qubits, targeted for delivery in 2029 from a quantum data center the company is building in Poughkeepsie, New York. The whole industry, meanwhile, has quietly changed the number it brags about. It used to be raw, physical qubits. The bigger the count, the louder the press release. Now the number that matters is logical qubits, the error-corrected workhorses, because everyone has accepted, after Willow, that reliability is the real currency. And new families of error-correcting codes, with names like QLDPC codes, are being developed precisely to build those logical qubits using far fewer physical ones, lowering the cost of the staircase. A clear-eyed reading of all this is simple. The wall is down, the path is visible, the machines are not finished, and the hardest engineering is still ahead, and the dates may slip, but the question has changed. For 30 years the question was, can this ever be made to work? After Willow, that is not the question anymore. The machine works. And those 3 words, which in part 1 were a calm and almost cheerful statement of fact, have quietly grown heavier as we have walked, because you now know what the machine does, and what it may be, and what it is being built to open. But there is one more turn in this part of the journey, and it is the most unsettling of all, and it has nothing to do with encryption. It has to do with knowing. There is a deep result in the theory of computation, established by the theoretical computer scientist Thomas Viddick and his collaborators, and it concerns the question of verification. Verification means checking the work. Confirming that the answer a machine gave you is actually correct. For an ordinary computer, verification is, in principle, always available. You can, if you must, trace the steps, repeat the calculation, audit the result with another ordinary computer. Viddick's work shows that for a sufficiently large quantum computation, this is no longer true. Past a certain scale, classically checking what a quantum computer did would itself require more time and more resources than exist. It would take longer than the age of the universe, more memory than the Earth contains. The work cannot be classically audited. It cannot be independently confirmed by the ordinary means civilization has always relied on. Sit with what that means. We are building machines whose answers we will not be able to check. The only thing capable of verifying the output of a sufficiently large quantum computer is another quantum computer, a second machine, just as strange, just as unauditable, working in the same way we cannot follow. We are constructing an infrastructure of trust around devices whose inner workings are, past a certain size, permanently beyond classical confirmation. We will run them, We will rely on their answers, we will encrypt and design and decide based on what they tell us, and we will not, in the old sense, be able to know that they are right. We will only be able to ask another oracle whether the first oracle was telling the truth. Think for a moment about how unusual that is in the long story of human tools. For all of recorded history, the instruments we built were, in the end, checkable. A telescope shows you something, and another person can build another telescope and point it at the same patch of sky, and confirm what you saw. A calculation can be redone by hand, slowly, painfully, but redone. The whole method of science, the thing that made it trustworthy, the thing that separated it from rumour and authority, rests on the idea that a claim can be independently verified by someone who does not simply take your word for it. Every instrument we ever made kept us, ultimately, in the position of being able to check. The sufficiently large quantum computer is the first instrument that may take that position away, not through malice, not through any flaw in the machine, through sheer scale, because the checking would require resources the universe does not contain. We will have for the first time a class of answer that we can use but cannot confirm, that we can act on but cannot audit, that we can trust only in the way one trusts an oracle, by faith in the machine and by asking a second machine, just as opaque, whether the first one lied. A civilization that builds an instrument it cannot audit has crossed a line, and the line was not crossed with a vote or a ceremony or even much public notice. It was crossed quietly, in cold rooms, by people in their 30s making coffee, while the rest of the world read the headline as a corporate horse race and turned the page. We are already on the far side of it. Part 10. The Argument in the Open. Now we arrive at the strangest part of tonight's story, and I have saved it for here, late in the journey, deliberately. It is not strange because of a new piece of physics. It is strange because of what it reveals about the people building the machines. Go back to December of 2024, to the announcement of the Willow chip. We have already talked about what Willow demonstrated, error correction crossing the threshold. But something else happened around that announcement, something that turned into a genuine public argument, and the argument is the thing I want you to see. Hartmut Neven is the founder and the leading figure of Google's quantum computing effort. He is not a fringe figure. He is the man whose team built Sycamore and built Willow. He is as close to the centre of this field as a person can be, and when Willow was announced, Neven wrote in plain language in a public communication that the chip's performance lends credence to the idea that quantum computation happens across many parallel universes. He reached openly for Deutsch's interpretation. He looked at the machine his own team had built and he said, in effect, "This is evidence that the other branches are real." That statement did not pass quietly. It set off a sharp and very public disagreement among physicists, and the disagreement is worth listening to carefully, because both sides of it are serious, and the honest position tonight requires you to hold both. On one side stand Neven and Deutsch, and those who think like them. Their argument is the one we have walked through all night, and it has real force. The machine works. Its calculation, traced honestly, involves more possibilities than the visible universe can hold. The cleanest, most natural account of where that calculation happens is the many worlds picture. The work distributed across branches of reality, the results brought home by interference. To them, every quantum computer that runs is a quiet experiment whose result is consistent with the multiverse, and Willow, by working so well, simply made the point louder. On the other side stand a great many physicists, and they are not cranks, and they are not enemies of quantum computing, and many of them work on quantum computers themselves, who say that Neven overreached. Their objection is precise, and it is strong, and you need to hear it. The many worlds interpretation, they point out, makes no unique experimental prediction. There is no measurement you can perform that comes out one way if many worlds is true, and a different way if it is false. Many worlds predicts exactly the same laboratory results as its rival interpretations, the same numbers, the same outcomes, the same everything. The interpretations differ only in the story they tell about what those identical numbers mean, and if a fast chip behaves exactly as every interpretation predicts it will, then the fast chip cannot be evidence for one interpretation over the others. Willow working beautifully is consistent with many worlds, but it is equally consistent with the Copenhagen view, and with the pilot wave view, and with several others. To call the chip evidence for parallel universes, the critics say, is to mistake a preference for a discovery. I am not going to stand here and tell you which side is right, because the honest truth is that this is not settled, and it may be the kind of question that the experimental method, as we currently understand it, simply cannot settle. What I want you to do instead is to lift your eyes from the physics for a moment and look at the situation itself, because the situation is the anchor of this entire video. So lift your eyes from the physics for a moment and look at the situation itself, because the situation is the real anchor of this entire video. Consider what we have actually arrived at. The most advanced machine in the history of our species has been built. It works. It works demonstrably, repeatably, and it works better every single year. And the people who built it, not philosophers musing at a distance, not commentators, not outsiders, but the physicists and engineers with their own hands on the device, the people who know it most intimately, cannot agree on what it is. One of them, the head of the effort, writes in plain language that the machine is a window onto other universes. Others, every bit as expert, every bit as serious, every bit as committed to the work, say that this is a leap the evidence does not license, that the chip working beautifully proves the mathematics and nothing more. They are all looking at the same machine, they are all looking at exactly the same data, and they cannot tell you, cannot agree, cannot say what it means. Feel the vertigo in that, because it is a genuinely new kind of moment for our species. We did not used to be here. For most of history, when we did not understand something, it was because we had not yet built the instrument, or run the experiment, or gathered the data. Understanding was waiting on effort. But this is different. Here the instrument is finished. The experiment runs every day. The data is in. And still, standing around the humming machine in good faith, the best minds we have cannot say what reality it is showing them. We built the thing that might finally answer the oldest question a thinking creature can ask. What is this place? What is it actually made of? And the thing did not come with an answer. It came with an argument. We have, for the first time, an oracle on the laboratory floor. And the oracle speaks, and we cannot agree on the meaning of a single word it says. That is the terrifying truth this video has been walking toward, and I want to say it as plainly as I can, because it is not the truth most people expect. The terrifying part is not that we have proof of the multiverse. We do not have proof of the multiverse. Anyone who tells you a quantum computer has proven the existence of parallel universes has gone further than the evidence allows, and you should hold on to your wallet. And the terrifying part is also not that the machines are dangerous in the way a weapon is dangerous, though the encryption story has real teeth. The terrifying part is subtler and quieter and harder to put down once you have picked it up. It is this. We have built a machine that works, that demonstrably, repeatably, undeniably works. And the fact that it works appears to be telling us something profound about the nature of reality, about whether there are other universes, about whether information is the true substance of the world, about whether space itself is stitched together out of entanglement. The machine is, in some real sense, an answer, and we cannot read it. We built the evidence before we built the framework to understand what we were proving. We have the result in our hands, humming in a cold room, and we do not have the key to it, and the smartest people alive are openly arguing about what it says. We are like someone who has received a letter, in their own handwriting, that they have no memory of writing, and who cannot quite make out the words. And I think it is worth saying, before we move on, that this situation is not a failure. It can feel like one. We're used to the idea that science marches in a particular order. First you understand something, and then, with the understanding in hand, you build the machine. The theory comes first, the device second. That is the comfortable shape of progress. What has happened with quantum computing inverts that shape. The machine came first, we have the device, working, on the laboratory floor, and the understanding has not caught up, and there is a real chance it will not catch up for a long time, if ever, in the full sense we would like. But look at the history of science honestly, and you find that the comfortable order is not the usual one. People built working steam engines and used them to remake the entire world decades before anyone understood the thermodynamics that explained why they worked. People used fire and bred crops and set bones for thousands of years before there was a chemistry or a biology or a medicine to say what was really going on. The machine arriving before the understanding is not an anomaly. It is very often simply how it goes. What is unusual this time is only the size of the gap and the depth of the question on the other side of it. The steam engine, once understood, told us about heat and pressure. The quantum computer, if we ever fully understand it, will be telling us about the structure of reality itself. The letter is harder to read than any letter before it, but we have at least received it, and that is not nothing. Part 11. The door marked simulation. There is one more idea we have to walk through before tonight's journey turns toward its quiet ending, and it is the one that tends to lodge in people most stubbornly, because it does not stay in the laboratory. It follows you home. It is the question of whether the reality you're sitting in right now, the room, the sound of this voice, the weight of your own body, is itself a kind of computation. The most rigorous version of this idea was set out in 2003 by a philosopher named Nick Bostrom in a paper with a deliberately blunt title, Are You Living in a Computer Simulation? Bostrom did not claim that we are. What he did was something more careful and, in its way, more difficult to escape. He constructed an argument with 3 doors, and he showed that at least one of the 3 must be true. The argument is called the simulation trilemma. Here are the 3 doors. Door 1. Almost every civilization like ours destroys itself, or otherwise comes to an end before it ever develops the technological power to run convincing simulations of conscious beings. Door 2. Civilizations do reach that level of power, but almost all of them, for some reason, ethics, boredom, law, lack of interest, choose not to run such simulations. Door 3. Civilizations reach that power, and at least some of them do run such simulations in great numbers, in which case simulated conscious beings would vastly outnumber the original, non-simulated ones, and a randomly chosen conscious being, like you, would therefore almost certainly be one of the simulated ones. Bostrom's point is that there is no 4th door. Logically, one of those 3 statements has to hold. Either civilizations like ours don't make it, or they make it and abstain, or we are very probably inside a simulation. For a long time, you could lean comfortably on the first 2 doors. Door 1 and Door 2 both rest, quietly, on an unstated assumption, that running a truly convincing simulation of a world, down to the behavior of matter at the quantum level, might simply be too computationally hard ever to be practical, for anyone, ever. If that were true, doors 1 and 2 would feel roomy, and door 3 would feel remote. And here is where quantum computers press on the argument. Quantum computers are the first concrete sign that simulating quantum reality at full fidelity may not be permanently impossible, that a sufficiently advanced machine could, in principle, model the quantum behavior of matter directly, because it is itself a quantum system. Quantum computers do not prove door 3. Let me be very clear and very honest about that. They do not prove we live in a simulation, and the argument remains philosophy, not physics. But they do something to the trilemma. They take a little of the comfortable roominess out of doors 1 and 2. They make the 3rd door harder to simply walk past. I want to balance that immediately, because intellectual honesty is the whole point of this channel, and the balance genuinely matters here. The strange physics we have spent the night exploring does not all point towards simulation. Some of it points firmly the other way. Remember the loophole-free Bell test from Part 5. Those experiments did not just prove entanglement is real. They also ruled out an entire class of simple models in which reality runs on tidy, pre-computed local hidden instructions. A naive simulation, the kind where every particle quietly carries a small script of pre-decided answers, is exactly the kind of thing the Bell tests slam the door on, to a confidence of better than 11 standard deviations. So quantum mechanics does not hand you a simulated universe. If anything, it tells you that if this is a simulation, it is not a cheap or simple one. It is a simulation that has to do the genuine, expensive, irreducible quantum work, the same work the cold machine in the cold room does. The universe, simulated or not, does not cut the corner. There is also a quieter reason to hold the simulation idea with care, and it is worth saying plainly because it often gets lost in the excitement. The simulation argument, even at its strongest, does not actually change anything you can touch. Suppose, for the sake of it, that door 3 is the true one, that this is in some sense a computation running on some unimaginable machine in some encompassing reality. Notice what would still be true. The warmth of the room would still be warm. The people you love would still be exactly as real to you, and you to them, as they have always been. The grief you have felt would still have been grief. The joy, joy. A simulated sunrise experienced from the inside is a sunrise. The argument, if it were true, would tell you something profound about the substrate your life is running on, but it would tell you nothing that demoted the life itself. This is the opposite of how the idea is usually sold. It is usually sold as a thing that makes everything fake. It is better understood as a thing that, at most, relocates where everything is real, and a reality is not less real for being hosted somewhere unexpected. So where does that leave the door-marked simulation? It leaves it exactly where honest inquiry should leave it. Open and unproven and impossible to dismiss with a wave of the hand, and also, this is the part worth carrying towards sleep, not frightening once you look at it steadily. A serious argument, pressed a little harder by the arrival of real quantum machines, and still, firmly, a question rather than an answer. You're not required to walk through it tonight. You're only asked to notice that it no longer has a lock on it, and that the room on the other side of it, if you ever did walk through, would look a great deal like the one you are resting in now. And noticing that is enough to carry us into the last stretch of the journey. Because if reality might be computation, then there is one more question waiting, and it is the most intimate question of all. It is not about the machine in the cold room. It is about the thing listening to this voice. It is about you. Part 12. The Machine in the Mirror. For the whole of tonight's journey, we have spoken about the quantum computer as something separate from us. An object, a device in a cold room, on the far side of a laboratory wall, doing strange things to reality while we stand at a safe distance and watch. That separation has been useful. It has let us look at the machine clearly. But near the end of the journey, I want to take that separation away, gently, because there is a serious idea, speculative, unproven, but raised by serious people, that says the wall between us and the machine may not really be there at all. The idea begins with a question that sounds almost childish. Why are we so sure that a quantum computer and a human brain are different kinds of thing? The standard answer is confident and reasonable. A quantum computer must be kept colder than the space between the stars, isolated with extraordinary care because its delicate quantum states are destroyed by the faintest warmth or disturbance. A human brain, by contrast, is warm and wet and electrically noisy and constantly buffeted by the chemistry of a living body. It is, on the face of it, just about the worst possible environment for fragile quantum effects to survive. So the brain surely is a classical machine, a magnificent one, but classical, and the quantum computer is something else entirely. That is the mainstream view, and it is probably correct. But two thinkers, the mathematical physicist Roger Penrose and the anesthesiologist Stuart Hameroff, have spent decades arguing that it might not be the whole story. Their proposal, it is called orchestrated objective reduction, ORC-OR for short, suggests that inside the neurons of the brain there are tiny structural elements called microtubules, and that within those microtubules quantum effects might be shielded just well enough and just briefly enough to play a genuine role in the process we call consciousness. I have to be as honest with you about this as I have tried to be all night. ORC-OR is not accepted science. It is a minority view. Most neuroscientists and most quantum physicists think the brain is simply too warm and too noisy for quantum coherence to matter to thought, and they have good reasons. There was a paper in 2022 in the Proceedings of the National Academy of Sciences reporting some evidence of quantum behavior in certain molecules inside microtubules at body temperature, an intriguing result and a fair one to mention, but it has not been confirmed at scale, and it does not come close to showing that consciousness runs on quantum mechanics. So hold this part of the journey lightly. It is the most speculative thing I will say tonight, and I am flagging it as speculation clearly, the way this channel always tries to. But hold it, even lightly, and feel where it points. Because if Penrose and Hameroff turned out to be even partly right, if the brain exploits, even a little, the same quantum strangeness that the cold machine runs on, then the wall we have leaned on all night would quietly dissolve. The quantum computer in its refrigerated room would no longer be an alien object we built and observed from outside. It would be a mirror. It would be a thing made of the same quantum fabric as the mind observing it, and the strangeness we have been describing, the superposition, the entanglement, the reaching across possibilities, would not be a property only of the machine. It would be a property also of the thing listening to this voice right now. And even if Penrose and Hameroff are entirely wrong about consciousness, even if the brain is purely ordinarily classical, recall what Wheeler told us in part 6, and the wall thins anyway. If information is the true substance of reality, then you, the listener, are already an arrangement of information. Your memories are information. Your sense of being a self, continuous through time, is information, held and updated and rewritten. The quantum computer manipulates information at the bedrock level. You're made of information at the bedrock level. The machine and the mind are not, in that picture, two different categories of thing. They are the same kind of thing, expressed differently. One in a cold cylinder of gold and copper, one in the warm dark behind your eyes. It is worth sitting gently with how strange that thought is, because it inverts something we almost never question. We tend to imagine that we are the observers, that there is the universe, out there, made of its stuff, and then there is us, looking at it, somehow standing slightly outside it in order to see it. The whole arrangement of tonight's video has quietly leaned on that assumption. The machine over there, us over here, watching. But there is no slightly outside. There never was. Whatever the universe is made of, branches, information, geometry, computation, you're made of the same thing, on the same terms with no exemption. You're not a spectator who wandered into the cosmos to have a look. You're a piece of the cosmos that has, astonishingly, folded around on itself far enough to wonder what it is. When you think about the quantum computer reaching across possibilities, the thing doing the thinking is itself a structure built from whatever those possibilities are made of. The observer and the observed were always cut from one cloth. The machine in the cold room is not the strange object in an ordinary world. It is an ordinary object in a world that was strange all along. And so are you. Somewhere in some branch, you made a different choice. We said that line about Hugh Everett early in the journey, that in his own theory, in some branch, the young man's idea was embraced and he grew old happy inside his field. But if his theory is right, the line does not apply only to Everett. It applies to the listener. If reality genuinely branches at every quantum event, then there are versions of this evening in which you're not here, listening to this, versions in which you chose a different video, a different room, a different life, branching away from this moment and from every moment behind it. Everett wrote that idea to explain the behavior of particles. He could not have known it would end up being a sentence about you. That is the strangest gift of this whole subject. It begins as a question about a machine, and it ends as a question about the person who was only ever trying to fall asleep to a story about the stars. Part 13. The Refrigerated Room. Let us go back now to where we began. Let us return to the cold room, because I promised you in part 1 that we would, and because it is the right place to bring this journey to rest. So let yourself be placed there, gently, one more time. You are standing in a room that does not appear on any public floor plan. The light is dim and warm-coloured, a soft amber that does not ask anything of your eyes. The room is quiet. From the ceiling hangs the cylinder we described at the very beginning of this journey, the chandelier built only of metal, plates of copper and gold suspended one below the next, each plate smaller and colder than the one above it. The topmost plate sits at 50 degrees above absolute zero, the next at 4. Below that, 800 thousandths of a degree, below that, 100 thousandths, and at the very bottom, on the smallest and most carefully guarded plate of all, the chip, a coin of engineered matter, held at 20 thousandths of a degree above the absolute floor of cold, colder than the space between the stars, colder than the faint afterglow of the Big Bang, colder than anything the universe, left to itself, has ever made. The only sound in the room is the slow, steady breathing of the pumps. There is no one here. There does not need to be anyone here. The chip has been running for hours patiently in the dark and the cold, and in those hours it has completed a calculation that, if the readings we have followed tonight are anything close to right, reached across more possibilities than there are atoms in everything we can see, drew quietly on the geometry of space itself, and operated on the informational floor beneath the world. It did all of that without drama. It did it the way it does everything, silently, steadily, at a temperature with no name in the natural world, and it is doing it still, right now, as you rest here listening. The machine is not waiting for us to understand it. It is not waiting for anything. It is simply, quietly, at work. A small, cold, humming point of the strangest activity in the known universe, tended by no one, in a room with the lights turned low. That room is real. Rooms like it exist right now, tonight, on 3 continents, while you lie here. The machines inside them are running while you breathe, and every reading we have walked through tonight agrees on one quiet, enormous thing, even as they disagree about everything else. They disagree about the big questions. Deutsch and Neven say the machine's work is spread across parallel universes that are every bit as real as this one. The skeptics say that is a leap, that the machine working proves only that the mathematics is correct and tells us nothing certain about other worlds. Wheeler's followers say the deepest layer of reality is information. The simulation argument leaves a door open that no experiment has yet closed. On all of that, the honest answer is that we do not know, and the people closest to the machines do not know, and the argument is happening out loud, in good faith, among the best minds we have. But underneath the disagreement, there is a single point where every reading meets. Every one of them, without exception, agrees that the classical picture of reality, the comfortable picture, the one almost all of us carry around without thinking, the picture in which the world is made of separate solid things sitting in ordinary space, each one definitely here and definitely now, and the universe you can see is simply all the universe there is. Every reading agrees that this picture is wrong, not slightly incomplete. Wrong at the foundation. It was only ever a local approximation, a comfortable story that works well enough at the scale of human bodies and human days, and that quietly fails the moment you look closely enough or build a cold enough machine. The disagreement among the physicists is not about whether the comfortable picture survives. It does not survive. The disagreement is only about how much stranger than the comfortable picture the true thing is. That is the real terrain. Not is reality what it seems. Every serious reading says no. The only open question is the size of the no. Part 14. The open question. So we come to the end of the journey, and I am not going to tie it off with a neat bow because the subject does not have one, and it would be a small dishonesty to pretend otherwise. Here is where we actually stand tonight, the 20th of May, 2026. There are machines in cold rooms that work. That is not in dispute. They perform calculations that the ordinary computers of the world cannot follow, and the honest tracing of those calculations leads to numbers larger than the visible universe, and the most natural readings of where that work happens point toward realities we cannot see, or toward an informational bedrock beneath the one we know, or toward a universe that is, at its root, something closer to a computation than to a lump of stuff. The machine works. It has always worked. We are only now catching up to it, and catching up, it turns out, is slow, because the machine outran our understanding before most of us even knew the race had started. Nobody has settled what the working of these machines means. Not Deutsch, who has thought about it longer than almost anyone. Not Neven, who builds them. Not the skeptics, who are right to insist that a fast chip is not a proof of other worlds. We have, as a species, built an instrument that seems to be answering the oldest question there is. What is reality actually made of? And we cannot yet read the answer it is giving. We built the evidence before we built the understanding. The letter has arrived, in our own handwriting, and we are still standing in the hall, holding it up to the light, trying to make out the words, and maybe that is the truest and the gentlest place to leave you. Not with fear. This was never really a frightening story, whatever the title promised. It was a story about wonder wearing a serious face. The ground you're resting on tonight may be the surface of one branch among countless others. It may be the projection of an information structure located nowhere you could ever point. It may be a computation, running somewhere that has no where. We do not know which. But here is the part worth carrying into sleep. None of those possibilities makes your life smaller. A self that persists across branching worlds, a mind woven from the same informational fabric as the deepest layer of the cosmos, a moment of awareness inside a reality far richer and stranger than the comfortable story we were handed. None of that is a diminishment. It is the opposite. It means the small, ordinary evening you are spending right now, listening to a voice describe a cold machine in a distant room, is happening inside something far vaster and far more astonishing than it appears to be. The machine in the cold room is still running. It will still be running when you wake, and the question it is quietly holding out to us, what is this place really? What are we really? Is not a question that needs an answer tonight. It will still be there tomorrow. It has, in a sense, always been there. We have only finally built something that asks it out loud. Rest well. The universe can keep its secrets one more night, and so can you.